All right, good afternoon, mathematicians. So we are just about finished with this unit of growing. There's one last thing that we need to talk about, and that is what we call decay factors or exponential decay. Okay, so I'm on lesson 4.1. This is on page 38. Our focus question is, how is the pattern of change in area different and similar to exponential growth patterns? And that should be a question mark. So how is a pattern of change in area different and similar to exponential growth patterns? And what this is in area, that refers to the problem in this lesson. So let's go ahead and take a look at what we're dealing with. So in problem 1.1, you read about the ballots Chen is making, right? So Chen was cutting a bunch of papers to make ballots, and notice that the number of ballots increased exponentially, right? So our question here says the paper Chen starts with has an area of 64 square inches, right? That's why our focus question is talking about area. We're looking at the area of the ballots now. So it starts with an area of 64, which we already input into this table for you. Copy and complete the table to show the area of a ballot after each of the first 10 cuts. So if we take a look at the pattern here, it looks at the number of cuts. When the number of cuts is 0, our area is at 64 square inches. When we make one cut, we are at 32 square inches. When we make two cuts, we are at 16 square inches. So the best way to go about doing this is we'll figure out how do you change from 64 to 32. What could you do? And most of you probably already assumed that, hey, we are dividing by 2. Okay? Now, I would say this is correct. However, we know that with exponential functions, there's a lot of multiplication going on. So to be consistent, and so that way you don't get confused, how can we write divide by 2 but make it a multiplication problem? Well, remember that if you divide by 2, it is the same thing as multiplying by 1/2. These two things are the same. So instead of dividing by 2, I'm going to multiply by 1/2. Okay, and does it follow the same pattern? To go from 32 to 16, if I multiply by 1/2, do I get 16? Yes, I do. And we're going to follow that pattern all the way for 10 cuts. So if I multiply 16 by 1/2, that should be 8. If I multiply 8 by 1/2, that's 4. Multiply 4 by 1/2, that's 2. Multiply 2 by 1/2, that is 1. Multiply 1 by 1/2, that's 1/2. And then we multiply 1/2 by 1/2, we get 1/4. We multiply 1/4 by 1/2, we get 1/8, and so on and so forth until we get 1/16 square inches. Okay, so here is our lovely table that represents the area of each ballot as we make more and more cuts. So how does the area of a ballot change with each cut? Obviously, if we were in class, we would have a discussion about this. If you could put it into words, what is happening to the area? Well, we need to write some complete sentences here. So the area decreases by half. Sorry, I'm thinking about the wording of this. The area decreases by half. Maybe I should say the area is split in half every time a cut is made. Yeah, let's say that instead, because decreases by half sounds like we're only taking half of a square inch off. So the area splits in half every time a cut is made. Now, what's nice about exponential decay is we're actually going to use the very same equation that we used for exponential growth, right? For exponential growth, we use this, y equals a, where a is our initial value, and we multiply it by whatever our growth factor was or is, and then that raised to a specific power. In this case, it would be one of our variables. They, however, want us to use a for the area of ballot and n after any cut. So let's see. So I guess our equation would be a right? The area of a ballot is equal to our initial value. Well, what did our ballot start out with? It's at 64. So 64 is our initial value, and we are multiplying that not by a growth factor this time, but by a decay factor, which we defined right here, right? The number that we are multiplying by every single time we increase the number of cuts. So we are multiplying by 1/2. So I'm going to use parentheses here. Multiply by 1/2, and then that is raised to the nth power. And there we have a lovely equation. Okay. So well, there is a significant difference here, but nothing is changing to the way that nothing is changing the way we write the equation there. All right, let's make a graph of the data. First of all, we need a title. We'll do. I'll be consistent here because we titled the table areas of ballots, so I'll title my graph that. Areas of ballots. Now let's go ahead and label my axes. So the x-axis, or the independent variable, is the number of cuts. And then our dependent variable is the area. And this is, of course, in square inches. Okay, and we need, how many spaces do I have? I think I have 10 perfectly. So that's 2, 4, 6, 8, and 10. And then area, we're going to have to be a little bit more creative. Right, so let's go, I'm going to say let's go up by 5. Well, I don't think that'll work. Let's go up by, sure, let's just go up by 5s. My initial value might not be on here, but got to work with what I have. Anyone watch Onward recently? Because that's where I got that from. Work with what you got. All right, there's 30, 35, 40, 45, 50. If I extend this a little bit, because I mean, our initial value is super important to include here. So there's 55, there's 60, and there's 65. Okay, now let's go ahead and plot our data. So at 0 cuts, we are at 64. I'll use a different color here. Let's use green. So really close right there. Then at 1 cut, we are at 32. Look at that drop already. At 2 cuts, we are at 16. So about right there, approximately. Let me make these a little bigger so you can see them. There we go. And then at 3 cuts, we are at 8. We're like there. 4 cuts, we are at 4. 5 cuts, we are at 2. 6 cuts, we are at 1. And then we get closer and closer and closer to 0, which you guys will learn probably in your pre-calculus classes in high school. All right, and then we draw a nice sketch of the graph there. And boom, there we go. There is our graph. So remember, you need a title, you need to label your axes, and then of course you need to plot your data. All right, let's keep going. Now here's your focus question. Sorry, I almost coughed there. How is the pattern of change in the area different from the exponential growth patterns? That should say patterns. You studied. How is it similar? Okay, so I want you guys to think about this problem because there are some definite similarities between exponential growth and exponential decay. There are also some definite differences between exponential growth and exponential decay. I'm going to make a discussion post about it so you guys can talk about it there. All right, so that was a little introduction into exponential decay, and I will see you guys in the next lesson.